Hello everyone. We will now begin our lecture on section 4 of chapter 3, which is on equivalent statements. Equivalent statements is an important topic in the study of logic. Two statements would be considered equivalent if, even though worded differently, they mean or imply the same thing. Now, to identify equivalent statements, we go through the process of constructing truth tables. And when we see that the truth values of each of the statements are identical, that tells us that the statements are equivalent. And identifying equivalent statements is important, has applications in real life. It helps us understand advertising claims, political statements, uh, the terms and conditions that we have to sign off on every now and then, as well as in understanding or deciphering legal documents. All right? So these are the topics that we are going to cover in this section. First, we are going to learn how to determine if two statements are equivalent. We are going to use De Morgan's laws for logic. We already spoke about De Morgan's law when we were learning about sets and Venn diagrams. We will learn to write conditional statements as disjunctions. Remember, disjunctions is the or statement, right? And then we will learn how to write the negation of conditional statements and then write variations of conditional statements, including some other concepts as inverses, converses, and contrapositives. So what is equivalent statements? Two statements are equivalent, symbolized by this bidirectional arrow or the three horizontal lines, if both statements have exactly the same truth values in the answer column of the truth tables. So when we go about identifying whether two statements are equivalent or not, we will first have to construct truth tables for each of the statements, and then we will compare the truth values in the answer column of the tables, and if they are identical, if the truth values are identical, they're exactly the same, then it is considered that the statements are equivalent. Now, if the answer columns are not identical, then the statements are not equivalent. And also, sometimes the words logically equivalent are used in place of the word equivalent. So we can say that either the two statements are equivalent or they are logically equivalent. They mean the same thing, right? Now here's an example to determine whether the following two statements are equivalent. So the two statements given to us, the first one P and within brackets Q or R, and the second one is within brackets P and Q or P and R. So the process of identifying whether the two statements are equivalent or not is to first create the truth tables for each of these statements. And once we create the truth tables, we are going to compare the truth values in the answer column of each of those truth tables. And if they are identical, the values are identical, that will tell us whether the statements are equivalent or not, right? Now here's the solution for example 1. We have the entire truth table before us, and this truth table is for both the statements given to us, right? So in the first three columns, we list all the truth values for P, Q, and R. Recall there were three statements altogether in both the compound statements that were given. So the number of cases that we will have for three statements would be 2 to the power 3, which is 8. So we have 8 unique cases to consider. And then we go to resolving the first statement. It's P and and then within brackets we have Q or R, right? So for the first step, we just list all the values, truth values for P. That's copy or whatever value we have in the first column into this fourth column. That's step one. And then we go to the column which is Q or R. So or is disjunction, and recall that for the truth table of R between two statements, the only time that we get a false in the OR operation is when both values are false, when both statements are false. So this time we are considering, or we are working with Q and R, these two statements. So true, true gives us a true, true, false gives us a true, false, true gives us a true, false, false results in a false. That's the only time that an OR will be a false. Then true, true is true, true, false, true, false, true again is true, and false, false is false. All right, so we got all the truth values for Q or R. Now we have to do the conjunction or the AND evaluation, but this time it's going to be between P and Q or R. So I'm going to highlight these two columns that we are going to work with. All right. So, and recall that in the truth table for and, the only time we will get a true is when both are true, when both statements are true. So we have to use that logic here. So let me pull up the pointer. So true, true should give us a true, 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 true and true should give us a true, true and true gives us a true, true and false gives us a false. So in the and statement, even if one statement is a false, the resolution is a false. All right, it results in a false. False, true is a false, false, true is a false, false, false is a false. All right, so this purple highlighted values is the result, is the answer column for P and Q or R. All right, so now we go to the next statement that was given to us. It's P and Q or P and R. Again, the same process. We'll start with P and Q. So let's look at the values over here. True and true should give us a true. True, true gives us a true. True, false gives us a false. This is an AND operation. Then we have true, false, 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 true, false, false, true, false, false, false is a false, and false, false is a false. Correct? So we resolve this, and let me highlight that with the color here, this, right? This is too dark, so let's get something lighter. Maybe this blue, right? Here. So this column, and then we have to go to the next column, which is P or R. Correct? So this time we are comparing P and R. So true, true, this is an and, correct? P and R, sorry. So again, true, true is a true, true, false is going to be a false. True, true is a true, true, false, a false. False, true, false, 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 true, false, and false, false, false. All right. And then we perform the OR operation. So again, true, true is a true, true, false, true, false, true is a true, false, true is a true, false, 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 false is a false, false and or false is also a false, 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 again a false, false, false is a false. Correct? So now we go and compare these two. All right, we compare the AND results with the OR results, and we see that they are identical. All right, you see over here, all the truth values are identical. So that means the statements are equivalent. All right. Now, based on the truth table that we constructed in the previous slide and comparing the truth values of the two statements that were given to us, which was P and Q or R, and the other statement was P and Q or P and R, we found that the final truth values, the truth values and the final answer were exactly the same. So we come to the conclusion that the two statements are equivalent. And we denote that using the symbol, which is a broad bidirectional arrow. Now we'll go through an exercise to determine whether two statements are logically equivalent or not. So the question says, determine which statement is logically equivalent to, it is not true that the tire is both out of balance and flat. And then they give us four statements, and we have to decide which of these statements is equivalent to the one given above. All right. So first, I'm going to break up the top sentence here into two simple statements or atomic statements, so to speak. There are two situations here, one that the tire is out of balance and the other that the tire is flat. So I'm going to first break it up into two parts, two statements. So let's do that. I'm going to denote the first statement as P and write it as P colon is the tire is out of balance, is out of balance. And the next statement will say, which is represented by Q, will say tire is flat. All right, tire is flat. And then I'm going to symbolically represent the statement, it is not true that the tire is both out of balance and flat. So we have an and situation here and a not statement here as well. So the way I'm going to write it is, it's not true, it's not, so the negation symbol, not true that it's both out of balance and flat. So within brackets, so what is out of balance? Out of balance is represented by the letter P. So P and Q, correct? So we're going to write it as P and Q. So that's a symbolic representation of the statement, compound statement given above. Now we will work through each of these statements and put them in symbolic form. The first one says, if the tire is not flat, then the tire is not out of balance. As we can see, this is a conditional statement. It's an if statement. And then let's see, what else does it have? It's a conditional statement. There's an if, there's a not flat, so there's negation. Then, of course, if then, the tire is not out of balance, right? So not flat is Q, right? So that's the antecedent. So that will come first. So if the tire is not flat, it's going to look like this here. The first part A will be represented as not if, but not Q, has to be written first, followed by the one directional arrow for if then, and then P, but it says not out of balance, so we have to negate P, right? P is that the tire is out of balance, but the statement here says not out of balance, so not P, not P. All right? Then we have part B, the second sentence, which says the tire is not out of balance or the tire is not flat. So this is not a conditional statement, but let's look at the different statements this has. So we have a not in this statement, and then we have an or, and then we have another not after the or, correct? So the tire is not out of balance or the tire is not flat. So out of balance is P. So we are going to write it as not P. So let me erase and rewrite. So not P or, right? This or represented by the V symbol, and then the tire is not flat, which is Q, not Q. All right. What about C? C says the tire is not flat and the tire is not out of balance. So again, we have nots in this, so there'll be negation, and we have an and statement also. So the tire is not flat, so not flat is Q. So not Q, and this downturned V to represent and. The tire is not out of balance is P, so not P, correct? And then finally we have the last statement here. It says if the tire is not out of balance, then the tire is not flat. So it's the reverse of what we had in A. It says if the tire is not out of balance, so let's circle the main parts here. If and then not, then we have a then and then again a not. But not out of balance would be P, right? So not P, and then of course the one directional arrow followed by not flat is Q. Flat is Q, so not flat will be not Q, correct? So these are the symbolic representation of each of these four statements. So we have to construct a truth table and evaluate their truth values, then compare it with the truth values for not, P, and Q above, for the statement above, with which we are comparing. And if they are identical, we can come to the conclusion that they are equivalent statements. So whichever is identical will be equivalent to the statement above. Now let's see how they worked out the problem step by step over here. Now recall that the first step is to take the given compound statement and break it up into two simple statements and represent them with letters, correct? So that's exactly what they do here. The compound statement had two simple statements. One is that the tire is out of balance, which is represented by the letter P, and then the tire is flat is represented by Q. Now in the next step, we will write the given compound statement in symbolic form. So what was the sentence given to us? It said, it is not true that the tire is both out of balance and flat. So the way we wrote it was exactly the way they have written it. There's the negation to start with for the first not, and then within brackets, it's out of balance represented by P. There's an and, so we have the and symbol followed by Q, which represents that the tire is flat. And then they will take the first of the four statements that followed, that's part A, and put that in symbolic form. So if the tire is not flat, then the tire is not out of balance. So this was a conditional statement, so it should have the one directional arrow. So let's pull that up. So it says not Q, so it begins with negation. So negation and then followed by Q, which is the tire is flat, correct? So if the tire is not flat, followed by the conditional symbol, and then the tire is not out of balance. So out of balance is P, so not out of balance would be negation of P, correct? And then we'll take part B and C of the four statements that were given to us and put those in symbolic form. So let's pull those up. So part B said the tire is not out of balance or the tire is not flat. So it was an or statement, but it was negation for both P and Q. So it was not P or not Q. So let's see if they have that. So yes, not P followed by the OR symbol, and then we have not Q. And then the third one was the tire is not flat and the tire is not out of balance. So for part C, it was an and statement, but both P and Q were negated. So when we write that in symbolic form, it should read as not Q because they have the flat first. So not Q and not P. All right. And finally, we need to put part D into symbolic form. So let's pull up the statement here. If the tire is not out of balance, then the tire is not flat. So this was again an if conditional statement. So when we write that in symbolic form, it should say if not P. So not P, negation of P, followed by the conditional symbol, followed by negation of Q. All right. So now we have to go and construct truth tables for all the 5 statements. So now we have the truth tables for all the statements that were given to us, the initial statement with which we have to check the equivalence, and then the 4 statements that followed below, the 4 choices. So we have the truth tables worked out for the topmost for the initial statement, so to speak. The final answer is under the negation sign here, negation symbol here. First, they had to evaluate. Remember, we always evaluate whatever is inside the parenthesis and inside the bracket. So what happened was we got the and let me take out my pen here, or the highlighter. All right. So first we had to evaluate P and Q and get the results here, TFF, and then we had to negate that, correct? So the final answer was put under the negation, which was changing the trues to a false, correct? The true became a false. Once we negated them, false became true, and we ended up with FTTT, correct? Then let's look at the truth table for each of those 4 statements. The first one was not if not Q, then not P, correct? So once we perform the evaluation of the truth table, we get for the if condition, it's true, false, true, true. Now let me just walk through quickly what happens here. We have our truth values for P and Q, all the combination of truth values to begin with, TT, TF, FT, and FF. And then first we have to negate our Q's for the first statement. We also have to negate all the P values, correct? That means negation means the true becomes false and the false becomes true, correct? And once we do that, we have to use the logic for the conditional statement, which gives us true, false, true, true, correct? So recall that in conditional statements, what happens is if the first if the antecedent, if the first statement is a true and the second one is a false, the consequent is a false, then we end up with a false. Otherwise, everything else is true. All right. So only TF will result in an F for conditionals. And that's what happened. We got TFTT. Now the next one here, the next statement was just an OR statement. It was not a conditional statement, but both P and Q had to be negated first and then the OR statement evaluated, and we ended up with FTTT. For the third statement, it was an AND statement, so we had to first negate all our Q values. It was not Q and not P, so we had to negate our Q's and our P's, P truth values, and then we had to find or evaluate the AND statements, the truth values for the conjunction, and we ended up with F, 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 T. And finally, it was another conditional statement, not if not P, then not Q. We ended up with T, T, F, T. And then once we complete the construction of the truth tables for all the statements, we go and compare which ones match the one above. Exactly. All the truth values match exactly as in the this table above. And we see, no, this one doesn't match, correct? This FTTT, this is the one that matches. Let's look for the other ones. FFFT doesn't match at all. TTFT doesn't match either. So FTTT, so the statement which is not P or not Q, that means if not out of balance or not, well, this is not an if statement, this is an or statement, so it should read as the tire is not out of balance or it is not flat. All right, so let's pull up the final answer. It says not P and Q. It is not true that P and Q is logically equivalent to not P or not Q. All right, so this is how we go about working on application problems to determine whether two statements are logically equivalent or not. So finally, to write the answer in words, it is not true that the tire is both out of balance and flat is logically equivalent to the tire is not out of balance or the tire is not flat. So you have to always write the final answer in words and not keep it in symbolic form. Now we'll talk about De Morgan's laws for logic. We had already visited De Morgan's laws when we were studying the set theory, the chapter on set theory. Now we'll come back to it and see how those laws apply to logic and truth tables. So these are the two De Morgan's law. It says not, and then within brackets we have P and Q is equivalent to not P or not Q. All right. And then we have the other one which says not, and then within brackets P or Q is equivalent to not P and not Q. And these are actually converses of each other, right? So let's look at this example here to use De Morgan's laws to write an equivalent statement. So the statement given to us is write a statement that is logically equivalent to it is not true that tomatoes are poisonous or eating peppers cures the common cold. So again, we will first break it up into two simple statements, also called atomic statements, and then we will write it in symbolic form. So let's see, let's do that here. It is not true. So just a second, let me pull up my pen. It is first we will of course have to write the two simple statements. So we'll call that P. All right, P says tomatoes are poisonous. So tomatoes are poisonous. And the other statement, we'll call that Q, is that eating peppers cures the common cold, right? Eating peppers cures cold. All right. So these are the two simple statements with which the compound statement was composed. So now we will put this entire compound statement in symbolic form. So it is not true, which means negation, negation. And then within brackets, we will have tomatoes are poisonous, which is P, all right? Or, there's an or here, so the or symbol followed by Q, which is eating peppers cures the cold. So it's going to read as not P or Q. Now, what would be an equivalent statement to this using De Morgan's law? So in De Morgan's law, what we do is we take off the brackets, all right? So, and we write it as, this is equivalent. So use the equivalent symbol here. The equivalent symbol, this would be equal to not P, all right? Not P. So you kind of distribute the negation to each of these statements. So not P and then not Q, all right? And this this or, all right, this or symbol changes to an and symbol. All right, this changes to an and that's De Morgan's law. So if we were to create a truth table for not P or Q, that would be equivalent to the statement not P and not Q. So let's go through the next slide to see if we are correct or not. So let's go through the process that they have come up with. It should be the same as what we got previously. First, they have broken up the compound statement into two simple statements, P representing the simple statement that tomatoes are poisonous, and Q represents the statement eating peppers cures the common cold, correct? And then they will put the statement given to us in symbolic form. So what was the statement? It is not true that tomatoes are poisonous or eating peppers cures the common cold. And that may be written as not, and then within brackets, P or Q, which was exactly what we got in the previous slide. So now let's go and see how the De Morgan's law is applied to come up with an equivalent statement. So when we apply the De Morgan's laws to come up with an equivalent statement, this is what we get, all right? So let me pull that up. So not P or Q, not within brackets P or Q, has an equivalent statement which is not P. So they negate, as I said, they kind of distribute the negation to both P and Q. They take off the brackets and distribute the negation to both P and Q, and they reverse the or to a and. All right, so the or statement becomes an and statement, correct? So therefore, the equivalent statement, we have to write the final answer in words. So how would we represent not P and not Q in words? Tomatoes are not poisonous and eating peppers does not cure the common cold. All right? Now we learn how to write a conditional statement as an equivalent disjunction statement. So disjunction means the or statement. So we can take a conditional statement which is if P then Q and write an equivalent disjunction statement, and the form of that disjunction is the negation of P, so not P or Q. All right. So to change a conditional statement into a disjunction, negate the antecedent. Change the conditional symbol to an or statement to a disjunction symbol and keep the consequent the same. All right. And so if we create truth tables of the conditional statement as well as this disjunction statement, not P or Q, we should get a truth table, or the truth values should be exactly the same, all right, making them equivalent statements. Now let's look at an example where we can write a disjunction statement as a conditional statement. So the statement given to us is the cows are in the pasture or the horses are not in the barn. All right. So this is the statement, and we see this is not a conditional statement. This is an or statement. So a disjunction statement. We have to rewrite this as a conditional statement which will be logically equivalent to the or statement. All right. So it says here the cows are in the pasture or the horses are not in the barn. So let's first break the compound statement into two simple statements. So I'm going to name P as cows in the pasture, and Q as horses in the barn, correct? So horses are in the barn, all right, in the barn. So when we write the given statement in symbolic form, the cows are in the pasture or the horses. So let me circle these here, or make that tells us it's going to be an or statement. So it's going to be P or, and then horses are not in the barn. So it's going to be the negation of Q, so not Q. So P or not Q is the symbolic form of the statement given here. Now, how do we convert this and rewrite it as a conditional statement? So remember, the rule is we take the P, all right, and that has to be negated, correct, in the conditional form, but the consequent, which is in this case not Q, stays unchanged, right? It's only the antecedent that will be changed. So we are going to write this as this here. Let me use a different color here. This P will be written as a negation. So not if not P. So we have to use the symbol for the conditional, which is the one directional arrow, and then not Q stays as it's, all right? So not Q. So it's going to be if not P, then not Q. All right, so let's go to the next slide and see if they have worked it out the same way as we have here. So we'll pull up the solution here one by one. Remember, the first step was to take the compound statement and break it up into two simple statements, atomic statements. So they have done the same here. They have represented P as the cows are in the pasture, and then Q is the horses are in the barn. That's exactly how we had broken up the compound statement. And the next step will be to write the compound statement in symbolic form using P and Q. So it says the cows are in the pasture or the horses are not in the barn may be written as P or not Q. And that's exactly the way we had also represented our the statement in symbolic form, right? So the next step would be to convert the or statement and write it as an equivalent conditional statement. The first step for doing that is negate the first statement, which is the antecedent, and then change the disjunction to conditional. So we are going to change this or to that one directional arrow, and we will leave not Q unchanged. Keep the second statement or the consequent part of it unchanged. All right, that will not be affected. So let's pull up here the symbolic form of the conditional statement. It would be if this symbol here for conditional should be read as if not P, then not Q. And that's exactly how we had concluded it. However, there's one final step. We have to write this in words, all right, with the using the words of the compound statement that we had been given. All right, so let's see. If the cows are not in the pasture, then the horses are not in the barn. So that's the way the final answer should come up with. We shouldn't just keep it in symbolic form. We should rewrite it and state it in words. Now we look into converting a negated conditional statement and rewrite it in an equivalent conjunction statement. So what we've been given here is not a negation rather of if P then Q. So first if P then Q is evaluated and then it is negated, and its equivalent conjunction statement is P and not Q. All right, so in this case, as you will see, that it's the consequent part of it, Q, is the one that gets negated and P stays as is. P remains unchanged. So let's work through an example in the next couple of slides and see how we can put this into practice in an application problem. Now, the statement given to us that we have to convert to an equivalent statement is, it is false that if you hang the picture, then it will be crooked. So we see over here, this is a conditional statement. There is an if-then clause here. And then there's also a negation because it is false, right? So we will work on this particular statement. So the first step is to break it up and write it as two simple statements and represent them with P and Q, all right? So let's see. We have two statements here, two simple statements. One is P, one we'll call one P, which is you hang the picture, right? You hang the picture. That's one statement. And let me add U anyway here. And Q is that it will be crooked. It will be crooked, right? So these are the two simple statements that we could extract from the compound statement given. Now let's put this in symbolic form. It is false means there's negation, correct? There's negation represented by the symbol here for negation. And then within brackets, we'll put here, hang the picture, which is P, followed by the one directional arrow for if then. And then it will be crooked is Q, correct? It will be crooked is represented by the letter Q. So we have the entire compound statement in symbolic form at this point, which is not, and then within brackets, if P then Q. All right. So if we were to convert this to an equivalent conjunction statement, this is what it would be. So let's put our symbol for equivalence. Equivalent statement would be P. All right. So it's P. Remember, when we are converting to a conjunction, it's the antecedent that doesn't get changed. All right. So it's going to be P and then followed by the conjunction symbol. And then it's the consequent that gets changed to a negation. So P and not Q. All right. So again, as usual, we'll go through the next couple of slides to see what the solution is and if it matches what we came up with. All right. Of course, we have to, at the end, rewrite the symbolic equivalent statement in words. All right, using the words of the compound statement given to us. So we'll pull up the solutions here. First step was to break up the compound statement into two simple statements, or what's called atomic statements. The P represents you hang the picture, correct? That was the first part of it. And then Q represents the picture will be crooked. All right. So these were the two simple statements that we extracted from the compound statement that was given to us. Then in the next step, we have to write the compound statement, which was, it is false that if you hang the picture, then it will be crooked. We had to write that in symbolic form, correct? And the way they have written it is not the negation followed by P, if P, then Q. And the equivalence of that is P and not Q. All right, so we got the same answer when we did the work in the previous slide. So now we have to write this, the symbolic representation in words of the compound statement. So we write it as you hang the picture and the picture will not be crooked. All right, so you just have to translate the conjunction statement that you came up with and write it with the and. All right, so it should say P represents you hang the picture, then the and followed by the picture will not be crooked. All right. Now we look into some variations of the conditional statement, and there are three variations of the conditional, which would be the converse, the inverse, and the contrapositive of the conditional. So in the next remaining slides, we will try to understand what each of these variations represent. Now here's a tabulation of the variations of the conditional statement. We have the name of the variation followed by the symbolic form of each of the variations and then how it should be read as. All right, so we start with the conditional whose variations we will look at. So the symbolic form of any conditional statement is written like this: if P, so P followed by the one directional arrow and then the P. This reads as if P then Q. And then the converse, the first variation that we learn is the converse. So converse is just switching the P and the Q. So in the conditional, the P was the antecedent and Q was the consequent. In the converse form, the Q becomes the antecedent and the P becomes the consequent. So if Q, then P. Q followed by the arrow followed by P. So if Q, then P. Now the next one is the inverse. Now in the inverse variation, both P and Q are negated. So if not P, then not Q. Right, that's how we read it. If not P, then not Q. And the contrapositive, the last one, which is called contrapositive, is really the converse of the inverse. All right, that's what it is. So over here you see they have taken the converse, they have switched the not Q as the antecedent and the not P in the inverse, which was the antecedent, now becomes the consequent. So in contrapositive, it's if not Q, then not P, read as if not Q, then not P. All right, so these are the three variations of the conditional. Now we'll go through an example of taking a conditional statement and rewriting it as first a converse, then inverse, and then a contrapositive. All right. So first I'm going to just write here what the converse, inverse, contrapositives are of a conditional statement that we just learned about in the previous slide. So the conditional is P, if P then Q, correct? If P then Q. So the converse would be if Q then P, correct? If Q then P. The inverse, all right, the inverse would be negating both P and Q. So if not P, then not Q. And then the contrapositive would be the converse of the inverse. So it would be if not Q, then not P. All right. So we have the conditional statement given to us as if the painting is by Andy Warhol, then the painting is valuable. Again, first step to break this statement up into two simple statements, correct? So P will represent, where should I write here? Maybe P will represent painting. The painting is by Andy Warhol. Painting, sorry about that. Let me correct the spelling here. Painting is by Andy Warhol. And Q would be the next part of the sentence, which is the painting is valuable. The painting is valuable, right? So the conditional form of this would be if P then Q, correct? That's the conditional form. So the converse of that would be Q, right? If Q then P. So how would we write that in words, or how would we say that in words? It would be if the painting is valuable, then it is by Andy Warhol. All right. The inverse would be not, so let's see, not, if not P, then not Q, correct? So how would we interpret it? How would we rewrite it in words of the statement? So if not P, that means if the painting is not by Andy Warhol, then the painting is not valuable, right? And then the contrapositive, which is a converse of the inverse, is not Q, right? Not Q. If not Q, then not P, correct? So how would we write that or say it in words? If the painting is not valuable, then it is not by Andy Warhol. All right, so again, in the next few slides, let's see how they have worked the solution. So here we go with the solution. The first step was to rewrite the compound statement in terms of two simple statements. So P would represent the painting is by Andy Warhol. That's exactly what we had also. And Q represents the painting is valuable. All right. So the next step after this would be uh, to write it in symbolic form, correct? So if the painting is by Andy Warhol, then the painting is valuable. So we just have to write the conditional of this, correct? So it would be if P, then Q. So let's look at the converse of the conditional. We have the two simple statements given to us that we extracted from the compound statement. So now we will just write the converse symbolically. So the conditional, which is if P then Q, would have the converse written as if Q then P. So in the next step, we will just rewrite the symbolic logic in words of this using the words in the statement, right? So the way we would state it is if the painting is valuable, you have to state the Q first as part of the if condition. So if the painting is valuable, then the painting is by Andy Warhol. Let's look at the inverse of the conditional now. So the conditional if P then Q has its inverse written as if not P then not Q. So when you put it in words of the statement, then it should read like, or it should read as, if the painting is not by Andy Warhol, then the painting is not valuable, correct? So that's what they have here. If the painting is not by Andy Warhol, then the painting is not valuable. And finally, we will look at how the contrapositive would be for the conditional. Again, the same two simple statements show up. The painting is by Andy Warhol is P, the painting is valuable is Q, and the contrapositive of the conditional, which is if P then Q, is if not Q then not P. In other words, it is the converse of the inverse, correct? That's what contrapositive is. So when we write it in words, it's going to read as if the painting is not valuable, whatever Q is, you have to negate that. If the painting is not valuable, then the painting is not by Andy Warhol. So you have to negate P as well, all right?